Hello? Oh, that might be better. Yep, so this is a Adventures in the Wacky World of Control Systems. It's mostly focused on the electricity industry because that's my background. We do cover various aspects of it. It's a grand bag of topics, so we cover all sorts of things in and about it. And we do other bits and pieces. The talk covers some of the challenges of the industry, and it will cover some of the things we've found and how, not necessarily the most exciting attack you can think of is going to be as good as you think it is, I hope. As discussed, I spent 15 years of software development at GE, mostly C and C++. I was the senior tech lead for the DMS product, which is a distribution management system. This is a software that controls the electricity at the distribution level, and basically controls the electricity from the primary substations you see in the outside cities, down to the secondary substations you see in your streets, down to the LV lines that go into your house. So it's not at all important, honest. Two interesting facts about GE before now. They were the 14th largest software firm in the world, but nobody knows this, not even GE, mostly because it's all acquisitions, which is interesting because no single software development team works like any other software development team. It also used to own an entire Class A subnet, so 3 dot was GE land. I decided all that was nonsense and moved to the dark side and became a security consultant with IOActive and have been here for 9 years. I presented on switches, which is industrial Ethernet switches, and some of the vulnerabilities found there, and at CS3 Stockholm, which is wind farm stuff, which we talked about. We will cover some of that material in here. Last time I was here, about 6 years ago, I did a talk on the history of connected control systems. I don't know if anyone's here from that talk, maybe not, but fundamentally they used to look like this. Now they look like that, and here's why. So beforehand, what we would have is an isolated control system. It was a proper air gap, nothing there. Security was physical locks on doors, all that good stuff, cameras and stuff everywhere. The problem was, certainly with the electricity industry, is you've got an attack surface that's measured in square kilometers. You have substations way out and all over the place, so they're all over the shop. The SCADA system was probably developed in-house by power engineers, so they knew their software implicitly. They understand everything about the software, what it does, why it does it, and how it does it. If anything goes wrong, they're the guys who are going to fix it. Communications network within the distribution management level was usually leased lines or their own copper. So they owned their own communication network. And the business side was entirely isolated. Keep it apart. Very much if it isn't broken, don't fix it mentality. You will find that in a lot of sort of the older industries, and particularly if you talk to a lot of control engineers, particularly the older ones, they're very much, no, this used to work, just leave it alone. We would refer to this as a legacy system now, but at the time, cutting edge, brilliant. Now it looks like this. So we have system vendors. So the power engineers that were writing the software up here in the first place have probably retired, moved on. The software, with the best will in the world, power engineers do not write well-engineered software. It'll do the job, but it's not maintainable in quite the same way. It's not extendable in quite the same way. The software engineering practices that we hope a vendor can supply are not necessarily there. So it becomes costly and unwieldy to maintain. So it becomes an idea for the company to go, well, let's go out to a vendor. We've got the likes of GE, hooray. Siemens, ABB all provide this software. So we'll get them to do it. Now the knowledge is no longer in here. The vendor knows it. And so to get that knowledge, they need their access in. So hopefully it's a VPN. Hopefully you just turn it on when you need it. Maybe, maybe not. There's a good chance now that the vendor has supplied your hardware, and now a lot of this has remote access capabilities, remote monitoring, remote stability. So you've got RTUs and substations that the vendor can dial into. The vendor has connection to the internet because all those software developers have to get their code from Stack Overflow somehow. The communication with substations have moved out. We now have smart meters in everybody's home. So you now have your control network is now in someone's home on a device that other people can physically touch. That's not necessarily under your control anymore. We'll talk about smart meters later. You now also have a connection to the business side, which you probably didn't have before. Couple of good reasons for this from the business point of view. There's a lot of useful information in here that business people can make good business decisions about. They can make operational decisions, they can make performance decisions. If they see that there's lots of faults at this substation, they'll go, well, let's go out there and do preventative maintenance before this substation catches fire. There may also be regulatory requirements. A lot of data in here that the regulators are really interested in. We'll get that out. The last point over here is the mobile workforce. There are field crews out, probably right now, working on the electricity network. They now have mobile devices to allow them to operate the device, to, in some cases, operate this equipment, not often, but communicate back and forth with the control network. We'll talk about that as well. In the future, maybe, there was a lot of talk about this lot all moving to the cloud, which is very interesting for all the wrong reasons. But instead, what we're seeing is a slightly more nuanced approach, is rather than taking the whole control system in the cloud, we'll take not so critical parts of it into the cloud. So a lot of the smart meter infrastructure. So how do we enable or disable smart meters? How do we gather that data? That tends to move into the cloud. What we're also seeing is that the backup systems for this are in the cloud. So a control network will have its primary system on a physical location somewhere, but if that goes down, they've got a backup system in the cloud. What was leased line or company-owned fiber is basically being replaced by the internet for cost reasons. You hope they get it right, and they put all the VPNs in. Maybe, maybe not. Anyone who's ever messed around with Shodan will probably stumble across a SCADA component somewhere out there. They exist, like it or not. So, the UK model. So, like I said, electricity network distribution model. So, in the UK, we have 9 distribution network operators, or DNOs. They basically are the companies that look after the switchgear in that region. So, it's the circuit breakers, it's the cables, it's the substations, it's all that good stuff that are in there. They're not necessarily the people you pay the electricity bill for. That's a completely different process. So you might be in here, which most of us are right now, and that's UK Power Networks. But you might be paying OVO Energy, or you might be paying npower or whoever. It's a virtual system, a bit like mobile phones work. They're regulated. Ofgem basically monitor the performance of these companies through a number of metrics, but the important one is one called CML, which is customer minutes lost. That's the number of, so for a given outage, so you lose the power, how many customers are impacted by that, times by the length of the outage. You sum that across the whole of the year, and whoever does really, really well gets a bonus. Whoever does really, really poorly gets a fine. So basically the fine pays for the bonus. The other interesting thing is within a given region, the physical switchgear, circuit breakers, earthing points, all the cables you see flying about, they're not allowed to have the same make and model and manufacturer throughout that entire network. They're allowed about a third. The reason for that is not necessarily for security, but it was originally for operational and safety reasons. If you deploy a circuit breaker and the vendor of that circuit breaker says, actually, it gets really problematic if it reaches about 35 degrees C. You don't want that impacting the entire region. So we have a third of it, so that if you have a problem, you can manage it, and if you're aware of the problem, you can reroute things accordingly. That's not the case for software. Apart from this little region here, all of mainland UK uses exactly the same distribution management software. So if you find a vulnerability in that, that impacts all of this, because that's not scary at all. What's interesting is that different DNOs have very different requirements as to how to deal with security. Some DNOs are very much, you must fix this. We found a vulnerability, go fix it now. Some DNOs are, okay, that's an interesting vulnerability, tell us about it, tell us how to mitigate it. What we want you to do is give us the operational functional requirements that we really need to make this work. Not that I don't care about security, I can manage security. I want you to give me the things that allow me to operate my network efficiently. There's one company doing this, right? Because it's one product. So they've got conflicting requirements from the customer. They've got new customers that they have to try and sell the product to. They've got new functionality put in. So there's a lot of time, and the typical sort of time pressures that software engineers just get. Bug fixing, all the rest of that. So this impacts quality, as with all things. So what sort of things are you going to find? It's software just like everywhere else. You are going to find cross-site scripting, SQL injection, crypto misconfiguration, all that good stuff. That's before you start messing around with ICS protocols. Input validation, buffer overflows, device stability. A lot of ICS devices are old. A lot of the protocols are really weird. If you are testing a control system and you're down at the I have to twiddle bits level before I find a vulnerability, you've probably missed rather a lot slightly higher up the tree. So let's talk about some specifics. Debug code. You probably can't see this, but remember when I said GE owns an entire Class A subnet, 3. So I'm in an isolated control room, on a test kit on an isolated control room, and the control system decides it wants to send a message to 3. GE land. That probably doesn't really want to do that. Bit of investigation, found out it was debug code to be left inside. Now, if you're a developer in GE and you're testing this all works fine. The QA department in GE test this all works fine. When it goes out to a control room, they're not really going to notice it until their firewall starts going, why am I talking to 3? So it would pass all the tests and it would get out. And if no one's watching the firewall rules, you're not likely to notice. Tweets. If you're sad like me, you might follow the distribution network operator's social media accounts. So UK Power Network social media account. Every morning, they'll ping a tweet out that says, hi, we're Dave and Sarah, we're from UK Power Networks. They might be, I don't know. And they will usually say, if you've got any problems or issues, give us a ping. And then throughout the day, they will ping out that we're terribly sorry for an outage in CO15 and give a postcode. They get that information from the control system. Control system knows the scope of the outage. It probably knows down to the postcode, potentially even the individual customers. So why not just have the control system send the tweet out? Sounds like a reasonable idea. Cuts out the middleman. There are a couple of ways you could do this. You could maybe have your control system talk to an interface, have that interface be a one-way outbound interface, have that interface talk to another backend system that sends a tweet out. Brilliant idea. Or you could have your control system directly connect to Twitter. Because that wouldn't possibly... You see, remember the network diagram about 3 slides ago? There wasn't the blue Tweety bird of Twitter on that for very good reasons. To my knowledge, nobody has enabled this feature for obvious reasons. DNOs, distributed network operators, like I said, grab bags or jump about from topics, are not in isolation. The different regions talk to each other, and they talk to the transmission network. They do this through ICCP. ICCP is the Inter-Control Center Protocol. It allows control systems to talk to each other, and it's possibly one of the most convoluted protocols out there. Why we do this? So within the distribution area, we have what's called microgeneration. So these are wind farms, solar. A lot of new houses have solar panels on their house nowadays. That's where that comes from. The traditional model used to be much more hierarchical. We would have big power stations up here, feeding into the transmission network, feeding into distribution, and that was it. This is now being slowly upended. So we now have generation happening here that feeds into the distribution network operator system. They need to know this because they do load profiling. So they can determine on a given day, roughly their load demands, how much energy they need to manage everyone, because everyone's electricity supply. So the lights stay on. So they know everyone wakes up at approximately 7, 8, 9 o'clock. Lights are going to go on then. They know for a given day when sun sets, so when there's light going to go on. They're also going to know this is when they start doing planning for like the FA Cup. So what time is halftime at FA Cup? So we can start bringing generation on because everyone's going to go and put the kettle on and go for a pee. Oddly enough, it's not putting the kettle on that's really the big drain on the electricity network. It's everyone going for a pee and flushing the toilets at the same time. Because it just, all the pumps suddenly have to wake up and flush all the water through. Anyway, so energy resources feed into the distribution network. They feed all that information up into transmission level in generation. So they can do profiling and they can work out, well, we need these generators to be online at a particular time. And because some generators can't just start immediately. It's really hard to start up a nuclear power station like that safely. Transmission level are going to work out that in some cases we don't have the capacity to manage this. So we need to talk to the DNO. We need them to turn on their wind farms. Or we need to talk to the DNO. We need them to cut off the power. This does happen. And so there's communication back and forth. And this is all managed through ICCP. Now, no island is an island. Our DNO, UK Power Networks, which covers here, talks to the transmission network. Our transmission network talks to, possibly hard to see on this diagram, Norway and France. France's transmission network talks to Germany's transmission network. Germany's transmission network talks to Poland. Poland talks to other Eastern European countries. They talk to... You can see how this might be troubling. Anyway, that's one thing. Mobile devices, bringing it right back to mobile devices. So, these field crew, they're out in the field working on the electricity network, probably tonight and probably in your region, turning off power and supply. They had, in the sort of before times, about 5-10 years ago, the process used to be something like this. Say, for example, in your area, someone needed to install a new substation. The control engineer in his control room would create a job or a schedule on the control system, and he would work out the operations he needed to perform. Which parts of the electricity network does he need to switch off and turn back on again, and which documents does he need to issue, and he creates a schedule and he works all this out in advance, usually 2-3 weeks in advance, maybe longer. Things happen, things occur. The scheduled operation and the time it actually starts occurring is usually a big gap. But the field crew at the time would have had a paper copy of the schedule printed 2-3 weeks back. So the operations go like this. On the day of the work, the control engineer rings up the field crew on the phone and says, right, I'm looking at version 4 of job 123X. And the field crew will say, well, I'm looking at version 3. Okay, so the control engineer will say, right, I need you to go on site and I need you to do step 1 and reads out the actual operations. Find this circuit breaker, open it. Step 2, find this safety locking point, safety lock it. Step 3, find this earthing point, blah, blah, blah. They read this out back and forth so everybody knows what's doing. The field control are now instructed to this specific state. Field control crew, the field engineers go out on site and they perform these operations. They then ring back to the control room to say, we have done steps 1, 2, 3, and 4. And the control engineer will say, that's lovely. I now need you to go on site XYZ and do step 5, reads the operation out. Rinse and repeat for hundreds of operations. This obviously ties up the control engineer. If he's dealing with one field engineer, he cannot deal with another field engineer crew. And obviously it's back and forth, and the field engineer crew cannot ring back to the control engineer and say, we've done our job, we're just sitting waiting. So why not give the field crew a mobile device that has a cut-down version of the software that shows them the network diagram, shows them the job as seen by the control engineers, so they're both in sync. Brilliant idea. What could possibly go wrong? By show of hands, how many people have lost a mobile device? Either laptop or phone or whatever. Okay, that's the obvious thing. We were asked during one of our tests, could we take this software and could we send to the mobile device the wrong network state so that the field crew are looking at a section of network that's potentially live, but they think it's dead because the network diagram shows it's dead because there's no safety implication in that at all. Then it's like, well, can we send out a job that doesn't exist? Yes. Here is IOActive's totally made up job. Instructing field engineer to go and find this oil switch and turn off all the power. This bug has been fixed, by the way, as have all the others. Don't panic, it's all fine. But these are some of the problems we face. Jumping topics again. Smart meters. So how many people, by show of hands, have a smart meter in the house? Pretty much all of us. Okay. So now we have something that's measuring our electricity usage in our homes, details of our personal life. So the obvious implication is privacy. And there's a not so obvious issue of upgradability. This is now a physical component in your house. If someone finds a vulnerability in that smart meter, how do they fix that? Can they do over-the-air upgrades? Is that safe to do? Is that secure to do? Do they send you USB devices that you have to plug in and it upgrades itself? Car manufacturers have done that. Does a guy have to come around and reinstall it? 52 million smart meters someone might have to upgrade. That's probably not a nice thing to do. Back to privacy. So the top paper, multimedia content identification. Someone worked out that if you had a live feed of someone's smart meter usage, they could map that to the brightness of the television and therefore could determine what you're watching on TV. Not a problem. The rollout of smart meters was stopped in Holland after a couple of privacy issues. The most interesting one was the guy who had his smart meter at home, thought this was brilliant, would check his meter usage from his office, check in, and then you would notice an unusual spike middle of the day. Didn't know what it was, went home during the day to find his wife was having an affair. Okay, so what, in the UK, just so we can all calm down, in the UK we take half-hour measurements, we don't take real-time measurements. But if you did have it, you can do profiling. So we have a real-time profile of someone's smart meter. From about midnight to 7 o'clock, the only thing that kicks in is a refrigerator. Hooray! I'm guessing they wake up at about 7 o'clock, pop the kettle on. Good idea. A little bit later, pop the toaster on, kick off the washing machine. Again, small spike at about lunchtime, and then stick the oven on, prepare dinner, have dinner for about 5 o'clock, I'm calling that, and then kettle 3 more times, and then bed. I'm guessing this person's British, by the way, by the amount of tea they drink. But that sort of information is available if we had that sort of level of detail. Thankfully, we don't. But you can determine, this is, obvious privacy implications. Another one just for comedy value. So this was a good few years ago, but the rollout of smart meters, they were going to have one decryption key in all 52 million smart meters. No, that's not a problem. Jumping topics again. Wind farms. One of the reasons I like control systems, SCADA systems, ICS systems, is that there is a physical component to it. There's a kinetic component to it, perhaps. If, for example, we're pen testing a bank and you get into the database that has everyone's account numbers, you can swap numbers about. So if I hacked into an account and say, managed to get David Beckham's bank balance, I could swap that number for my number, which is not quite as much as David Beckham's. Not far off it, but not quite as much. But the bank could just put those numbers back, no harm, no foul. As we'll show in the next few slides, if you change numbers in the control system, putting the numbers back is not necessarily going to fix everything. Now, regardless of what you think of this fella, you might think, well, who's going to attack a wind farm in the first place? There are a number of potential causes as to why people might not. You do have the political point of view. You do have oil, coal, and gas have their vested interests. You have the bird watchers, you have environmentalists who are worried about blade strike hitting birds and all the rest of it. You have very subtle issues environmentally where behind a wind farm, you have now changed potentially the microclimate. So if you've got a very sensitive area behind that, that gets impacted. You also have to clear, large areas of land. You have to chop down trees to be able to stick these wind farms in or isolate off a large area. So there are people who are not necessarily for this sort of thing. And even if it's just a visibility thing, I don't necessarily want to see one of these things in my back garden, perhaps. So, if one could take over a wind farm, what could you do? Well, the blades that are installed have a vibration limit. Unfortunately, we can't measure this until it's properly installed. So you actually have to build the turbine, put the blades in place, work out what those limits are. You can then set that limit in the software, because there's no other way of doing it. But if you have access to that software and you swap the numbers, it breaks. Swapping the numbers back is not going to unbend that blade. Turbine overspeed. They spin quite fast. It gets quite warm in there, even when it's spinning slowly. Again, limits and controls are in the software. We have control of the software. We disable those limits. It goes bang. Putting the numbers back is not going to unbang that turbine. It's dead forever. Lubricants. The turbines spin. They have to spin smoothly. There's pumps and lubricant tanks in there. If you can find a way of disabling that, or if you can just drain the tanks, again, that's going to have the same problem. Spinning metal that is now grinding. Other silly things you'll see, wireless access points. Who wants to get into the bottom of the turbine, climb all the way up to the top just to plug yourself in, when you can do it from wirelessly? These are usually during the deployment phase, they're in place, and you hope that people turn them off. But if you can just rock up in your car, park yourself, get a high gain antenna, connect to them, brilliant. More physicsy stuff. Wind turbines, some wind turbines produce DC current. The rest of the world talks AC current, here at 50 Hertz, US 60 Hertz, whatever. So there needs to be a big converter, usually on the wind farm, that will convert that DC into AC. You get the phasing wrong, so you don't bring it on at 50 Hertz, something goes bang. Similarly, you have problems with AC turbines. You have a turbine that's running AC, but if you bring that individual turbine out of sync with the rest, there's torque in that, and that can bring either the turbine up to speed or down to speed very, very rapidly in a way that breaks it. This shows a couple of things. The issue of the wind behind the turbine being turbulent and therefore affecting microclimate is the obvious one. The not so obvious one is what's referred to as wind shadow. In fact, that's a terminology for it, is so that this wind is all turbulent behind the first blade. So the next 2 or 3 blades are not getting nice clean air. So when it's spinning, it's not getting nice air, and therefore that can create resonance. This was a problem in a lot of the earlier wind farms because nobody really understood this problem quite so well. So what they now do, certainly with the older ones, is they will work out if the wind's blowing in a particular direction, they will disable the turbines behind the leading one. Again, that's in the software. If you can control the software, you can turn it off. Last sort of issue, particularly in the colder regions, you will get ice buildup on the turbine blades. That ice buildup is not uniform, and it's not uniform across an individual blade, far less 3 or 4 blades. It changes the shape of the blade, it can cause rotational imbalance, so the thing starts shifting as it spins. You don't want that. So a lot of them have sensors in, so they can work out when they've iced up, and sometimes they will just stop, and you have to come along and de-ice it. Some of them have radiators in, and they will sort of stop, go through a heating cycle, melt the ice, and restart. Brilliant. If you can mess with the sensors, you can do a couple of things. You could constantly make it stop, so it always thinks it's iced up, even when it isn't, or you can make sure it doesn't stop at all. Spins with big chunks of ice on. What could possibly go wrong? So we've done a couple of assessments of wind farms, and so the obvious 2 things to deal with wind farms is physical security. In this particular example, it's just a lock on the door. It's not just a lock on the door, it's a remote location, and in fact it's guarded by hibernating bears. But that's by the by. Some wind farms, it's just locks on doors. Other wind farms, you will have security cameras, you will have motion sensors, all that good stuff. It really depends on the location, where it is, and what the company believes the risk model is. For example, this wind farm is about 2 hours away from the hotel. That car was clean when I left the hotel. It would have been worse a few months later when all this would have melted. Okay, so the wind farms are usually in remote locations. How do we connect to them normally? Well, we would do that remotely via VPN. So let's test out the VPN. How many people have seen or used Shodan? Excellent. Shodan, for the rest of it, you didn't stick your hand, is a search engine that doesn't tell you what the contents of the internet are, it tells you what the actual machines are. So basically it's a large Nmap scan. It doesn't use Nmap, but it uses something similar. And it gives you all the ports and services and computers and makes some models that connect to the internet. This is a Shodan scan of a VPN host of a wind farm. It's probably hard to read, so I'll read it for you. So it lists the number of ports across the top. We'll get to the vulnerability in a minute. Don't worry. Port 22, SSH. Brilliant. That's really, really useful. Port 23, Telnet. Not so much. 1881 is HTTP, obviously. 2002 is the VPN host. And 3389 is terminal services. Which leads us nicely to this. So Shodan is well aware that this VPN host has a terminal services vulnerability. Remote code execution can get you onto a wind farm. Now, there's nothing in here that says that this is a wind farm. It's just an IP address. You might be able to determine its location. Geolocation is not that brilliant, but it will give you certainly an area. What's even more interesting is the host behind this one. So you can hop onto this one using terminal services. The host behind that is vulnerable to Eternal Blue. And then from there, the rest of the wind farm is yours. Did another assessment of a wind farm that was deployed and built in 2013. The year is particularly important because it had MS-08067 in it. That's a 5-year-old vulnerability, just deployed. Couldn't possibly be a problem with that. So, wind farms in the grid. So we've shown that the electricity network is completely broken. Maybe. So, as an evil hacker that we all are, if we were to control the electricity network, what could we do? Mwahaha, let's turn off all the lights. Is not the most exciting thing you can do. I will show you why, given this nice example. How many people were during the 2019 blackout? You were? Okay, so 1 or 2 people were. I wasn't. I was in Scotland, ignoring it. But basically, what happened is a storm occurred. There was a lightning strike just here, west of Cambridge. That's nice. A wind farm way off in the North Sea decided that's too much for me and tripped out. And a power station just here tripped out as well. Basically led to 16,000 megawatts lost. And the way they resolved it is turn off 1.1 million customers and then brought everything back on. We'll give you a timeline. So, on the day in question, at 16:52, lightning strike hit 400 kilovolt line. So it's a high voltage line. At 3/4 of a second later, the wind farm tripped. So there's a bunch of protection equipment before all this gear to stop wind farms from breaking, or indeed any piece of equipment from breaking. Basically monitors jumps in voltage, changes in frequency, and this gear basically stops badness from happening. So, trips, we've lost power from the wind farm. At the same time, one of the turbines at Little Barsford, just that far away from the lightning strike, if we remember correctly, that trips as well. That's about a second after the lightning storm. So we've lost 1,000 megawatts of power. A few more trips, we're down about 1,400 megawatts. Now, what we like to do in the electricity network is we like to keep the generation at the same level as the load. So how much electricity is being used matches the amount of electricity we're generating. So we've now just lost a chunk of generation. There are 2 things we can do. And the first thing we've tried to do is bring on more generation as best as possible. So this is when we turn on the wind farms that we have access to. We turn on hydropower because it's really easy just to open the floodgates and let water pour through and turn turbines on. Not so easy to warm up a gas power station. But that's what they try to do. The frequency drops out to 50 hertz. The problem with that is that will cause other things to break. So as it drops, first thing to do is bring more generation on because you don't necessarily want to disconnect customers. That would be a bad thing. As a result of this, the second generator, Little Barsford, trips. So that's about a minute after the lightning strike. So we're now down to 1,600 megawatts lost. The frequency goes to 48.8. Now, it doesn't sound like a lot, but everything running at 50 hertz is really, really important. So the transmission network basically said, no, we can't bring generation on fast enough. The safest thing to do is disconnect 1.1 million customers. So that's when London and chunks of the southwest went dark. About, 16:53, 5 minutes later, having turned everyone off, the frequency is restored to 50 hertz. So what they've done, generation dropped, load's still up here. We tried to bring generation back up, that wasn't going to work, so we just dropped the load. That then restores everything to 50 hertz, and then we can slowly start bringing everything back on. So about, 40 minutes after the lightning strike, we had restored distribution. So even Mwahaha person turns off power. 40 minutes later, someone's going to turn it back on again. That's what this shows. Now, it wasn't quite as simple as that for those who were in London at the time. I think 9th of August also happened to be a Friday, and this is obviously rush hour. So what happened is power went off. There's a lot of train electrification around this neck of the woods, and quite a few of those trains wouldn't restart. The only way you could restart them is to pull out a diesel train, plug it in, jumpstart, and keep going. The trains that were able to run were stuck behind all these dead trains. So that's where a lot of the chaos came from. The US blackout. This was slightly less well organized, but this is a combination of two issues. The UK issue was purely a physics issue. Lightning strike, things went out. This is a combined software issue and physics issue. So the bit of software that sort of monitors the US market is a piece of software called X821, and within it there was a race condition. This race condition, if triggered, meant that the software wasn't processing alarms. So an alarm is something unusual happening on the network. Something unusual happens on the network, they don't see the alarm, they don't know what's going on. At the same time, the companies in question had been remiss in trimming back lines from the power station, from the power lines. So the trees were touching the lines, caused a trip out at a time that they had no visibility of what's going on, which led to a 14-day outage. Slightly more than 20 minutes the 40-50 minutes we suffered. So what happened? Again, timeline. So at roughly 2 o'clock, the first high voltage line fails out, tree has touched it, circuit breaker trips, just to protect the rest of the equipment. At about 2:15, the race condition triggered. We're now no longer seeing unusual events in the network. Loss of visibility. We don't like that. Half hour later, the system fell over, effectively, and went to the backup system. Now we're taking about a minute to see any changes to network state. Half hour later, or between then and sort of 3:15, we're getting a voltage dips on the line, and the operators aren't doing anything because they're not aware of anything going wrong. 3:30, the second high voltage line trips out. The operators do not inform their neighbors. In the US model, there's a lot of communication because they have much smaller regions, and so they all talk to one another. So if something like this occurs, they can talk to the other region and transfer load and manage it that way. At 15:41, an interesting time, a circuit breaker trips, taking out 15 medium voltage lines, or 138 kilovolt lines. There's no alarm generated. The control system and the people operating the control system are not aware of it. Their neighbors ring them up and say, do you know if something's going on? I went, no, we're not aware of anything. A minute later, they lose power in the control room. Everything goes dark. And then they're sort of aware of what's going on. At 4:05, the third high voltage 240 kilovolt line trips. Prior to this point, 2 hours of lack of visibility, they could have restored and wouldn't have had the subsequent problem. That trips out. The next 5-10 minutes, as cascading power failure, takes 256 power plants offline, and you have this area of darkness for 14 days. So, this case, evil person does bad thing, but everyone just turns the lights back on. Not that exciting. Changing topics. I don't just do electricity, you'll be pleased to know. I could talk for hours about electricity, and I've done a good chunk of time already. We do ships and boats. Again, there are control systems on this. Power, steerage, electrical generation, water reclamation, all that good stuff. You will also have ship management, navigation, logs, all that interesting stuff. And you will have crew internet connection via satellite, so they can do things in their downtime. You also have onshore connectivity to a vessel, so they can do administrative things. What we find in these environments is exactly the same thing as you'll find in any other network environments. You will find poor and default passwords. You'll find incorrect firewall rules. You will have network connectivity where network isolation is configured. You will find, it's not perfect. In one instance, we were testing network switches that actually allowed for an unauthenticated reconfiguration. So all the hard work put into isolating the network, you could just go in and unisolate it. What can you do? Dogs. So they transport crates about the place. They get picked up and dropped on, and people drive away with them. What you find, certainly in the newer environments, is a lot of this is wireless infrastructure. So all your good wireless attacks, deauth attacks, all that stuff works. Again, poor network segmentation. We were on site, we were testing what we believed to be the right IP address range that we were given, And the doc, about 5 miles upstream, rang us up to say, please stop pen testing our network. You should be on this network instead. What can you do? Couple of interesting things. A lot of these cranes are not really manned. There's a control room about there, and it's all cameras and it's controlled via joysticks and bits and pieces. And they have a bit of software that's a scheduling bit of software. By scheduling, I don't mean this boat's going to turn up on Tuesday. What it does is it works out the order in which you have to load these crates or unload these crates on this boat so it's not going to tip over and collapse. So if you get control of that, and you can maybe put all the heavy boats on one side, you can tip it over. Don't want to be doing that. Last thing, because this was in terms of properly wacky. So these are devices, or devices like this they use at ships on docks to scan in and scan out the crates as they come in. And so they run Windows and they run the software in a kiosk mode. So the operators can just use this software, that's it. To administer them, they had an open FTP server that allowed anonymous access. So we just poked in, jumped on, gave us access to the complete C drive, no problems with that. So we found the kiosk software that they ran, deleted it, and rebooted it. Windows! Hooray! Right, final thoughts. So, within the control system industry, regardless of whether it's electric, gas, oil, a small farm down the road, or whatever does control software, you will find a lot of the same issues in any other industry. The impact, however, might be slightly more kinetic. You change numbers, turbine blades break. You put numbers back, that's not going to fix it. But you're going to find safety systems in place. A lot of, certainly for the electricity network, there's a lot of protection gear in place to protect the hideously expensive gas turbine from blowing up. So the circuit breakers trip out to stop that from happening. In chemical factories and other sorts of factories, you'll find isolated and independent safety systems that go, hang on, it's getting a bit warm in here, and shuts things down. And the obvious attack might not be spectacular. Wahaha, I have the electricity grid in my hands, I'll turn the power off. No, we'll just get guys on site, we'll just turn the power back on again. However, I like to think that this is all lovely, but maybe our dear friends the Amish have the right idea after all. Thank you very much.